Hello everyone, my name is Lou from GameCode Plus, and today we're going to go over coroutines in Unity. The goal of this lesson is to give you a deeper understanding of coroutines and help you to use them correctly. So let's move forward and start this lesson. For this lesson, I'm going to do a lot of demos in code, but I'm going to use the slides as starters just to kind of explain base concepts before we get too deep into the code. So our lesson plan. First things first, what is a coroutine? How are they used in Unity, and what benefits do they provide? Next, we're going to go over ForEach loops in C#. It's going to be a very simple oversimplification, really, of ForEach loops, something quick that we can cover just so that we can move on to how iteration works. Then we'll start with what is the yield keyword? What does it add to iteration? How does it work in benefit with ForEach loops? And really, how can we use it to better our own code? And then next we'll be going over the IEnumerable and IEnumerator interfaces, how they're used by coroutines, and how they can be used outside of coroutines for that matter. And then finally, we're going to actually write a coroutine library from scratch in C#. Not using Unity at all, just writing it directly in Visual Studio, just so that we can understand behind the scenes how it is that Unity is using coroutines and what it's really probably doing. Now, keep in mind that there are certain examples in this course that I'm going to have oversimplified, and there are also certain expectations that I don't have the source code for Unity. I'm not showing you exactly what Unity is doing behind the scenes. I'm just showing you how it could work behind the scenes, and probably an oversimplified view of it so that it's easier to explain. So let's start with what is a coroutine. Well, a coroutine really is Unity's way of providing single-threaded multitasking. So what is single-threaded multitasking? Well, single-threaded multitasking is the ability to allow many tasks to run and share the same thread. So the way that works is that each task is given a small time slice each cycle in order to run its processing, or each frame. So if you've heard something like 60 frames per second for a video game, for example, that means that every second, 60 loops of some processing have happened, and in that frame usually there is some render to the screen that typically ends the processing. So 60 times per second they're rendering to the screen, but in addition, oftentimes, they're also doing many other processes in each one of those frames. So in that frame, they might be running one task that, let's say, for example, updates the position of the player on the screen, and then another task that calculates some physics calculations possibly related to that positioning. Another one might have to do with some user input or highlighting, and then rendering and so on. So one way that this can be achieved is that each task is given a call that says, okay, do some work, and then that task itself determines when it has done enough work for this particular time slice, and then it returns back to the caller. And then the caller itself says, okay, next task, do some work. And it does that over and over and over, and it just keeps on doing that forever. So that's each loop would be your frame, and it would do this continually. And that's what coroutines really help you to do. So let's move forward and show a demo of coroutines in Unity. So I prepared a very simple Unity project. This is a 2D project. I have a camera pointing at a sphere in 2D space. So this is what the camera looks like at this point. If we run this, what we'll see is there's our sphere in the middle of the camera space, and nothing's really happening. And if I hit spacebar, now we can see the ball, in this case, or the sphere, animating from left to right. And that's being done with coroutines. So let me show you how this particular code works. So on the sphere, we have this sphere animation script. So if we look at that animation script, there's a few things here to take note of. I'm not going to go into most of this in detail. If you feel that certain parts of this would be beneficial for an entire video, let me know. I can go over them. But we have a few variables defined. We serialize a few fields. So we serialize the left edge of the screen, that's -5, the right edge at +5, and a time scale, in this case 10. And then we set a flag, a Boolean, that says whether the current animation is active. So if you remember, at the beginning, we didn't have the animation active. And then when I hit the spacebar, the animation became active. And the way that's done is there's an update method here. This is a Unity message. It's called every frame. So on each frame, Unity is going to call this code. And in this code, I am checking to see if the spacebar is pressed. And if the spacebar is pressed in this frame, then the animation active is going to be set to the opposite of whatever it was before. So let's say it's currently false. It's going to say animation active equals not false. Well, not false is true, so animation active is going to become true. And the same thing could be said the next time around. If I push it again, it would say animation active equals not true. Well, not true would be false. So after we update it, it then checks. If it's true, we start our coroutine called animate motion. This is Unity's method, start coroutine. It takes a method, or it takes a type of IEnumerator, which we'll get into shortly. So this animate motion method returns an IEnumerator, and if animation active is false, then we're going to stop all coroutines. And what that does is actually stops all coroutines on the given component. So anything running in this class, any coroutines that we've started using start coroutine, it will stop all of those. So let's look at what animate motion does, and just look at a few specific details so that we can go into more depth on those as we move forward. So the first thing to take note of is animate motion is a method that returns an IEnumerator. Now this is required for coroutines in Unity, and we're going to get into this much more deeply as we move forward as to why that's required. But just make note that any coroutine must return type IEnumerator. Now next, we have some code. We'll go over that quickly in a minute. And then somewhere in the method we have a yield return, for example. So in this particular case, we're yield returning a new wait for end of frame. So we're creating a new object of type wait for end of frame, and we're returning that via yield. That is something also that we're going to be going much more in depth on, but keep in mind that a yield is required for every IEnumerator, well, for every coroutine method in Unity. So we're going to yield return something from every coroutine. So in this particular case, we can go over very quickly what happens. So we're looping forever. That's the outside for loop. We're setting a variable of type float. That's a t. We're going to update every frame, the amount of time that changed that frame, and we're going to do some linear interpolation for what the current position of that object should be, and update the x position based on that linear interpolation. And then we're going to yield for the end of the frame. Yield return new wait for end of frame. And this is going to allow us to come back every frame and update the position as we move from left to right until we hit the right edge. And then once we hit the right edge, we're going to do the exact same thing as we move back to the left until we get to the left edge, and then continue right edge to left edge over and over and over. So that's this very simple coroutine example. We're going to go much more in depth on all of these things as we move forward, but hopefully that just gives you an idea of something you could do with coroutines if you haven't used them before, and an idea of also how they look on screen and in code. So let's talk about the for each loop in C#. So this is going to be really simple. I assume at this point that most all of you have some idea of what the for each loop in C# is doing. But realistically, the for each loop enumerates the elements of a collection and then executes a code body for each element. So let's look at this example. So we have for each int item in item collection. So item collection in this case is some collection of integers. Let's say, for example, it's a collection of the first 10 odd numbers. So in this case, we're going to say for each int item in that collection of odd numbers, we're going to call this method console write and then the item. So we would come through the first time and we would call write and then a 1, since that's the first odd number. And then we would get to the end and we'd come up here and then we would write 3, and then we would write 5, and so on. So that's a real simple example of what a for each loop can do. So let's move forward and show an example in Visual Studio of a for each loop that will help with the explanations as we move forward with our coroutines. So I've tried to build each one of these off of the top of the previous, so we're going to start with a really simple for each test. So in this test, we're going to run this method. So we're going to loop over all of the items that are returned by this method, which are going to be of type test class, and then we're going to call the console write line with the current time and date, and then that object. So if we look at what that method does, that method returns an IEnumerable test class, and we build it up inside. So in this case, we're using a list of test class. So list is IEnumerable, so anything that can be enumerated over will oftentimes implement IEnumerable. So a list or a hash map or a dictionary. Dictionary is not the best example in this case, but anything that can be iterated over, a list being a good example. So what we do is we say, okay, we're going to create a new list, and then we're going to loop through the first 10 items from 0 to 9, and we're going to construct a new test class by giving it that item, and then we're going to return that whole collection, that whole results list, which is of type IEnumerable because list is IEnumerable, back to the ForEach. And then the ForEach is going to go over each item and call this write line. And if we look at that test class, it's really simple. I only did this so that later I can make an adjustment. But we pass in a variable I. We store that variable I, and then in our toString, when we go to print it, we print test class dash, and then the variable that we had stored, in this case, I. So as we go through, it's going to be 0, 1, 2, 3, 4, 5, etc. So if we run this quickly, I think probably at this point everybody should have a pretty good expectation of what we're going to see. So if we run it quickly, here's what we see. We see starting test, which comes from the program code itself, and then the date and time, 3 dashes, and then the object itself, which comes from this toString method here. So test class dash, and then the number that we passed initially in the constructor. So for each item of these 10 that we returned, loop over each one and write to the console the time and the object. And you can see this happened at more or less the same instant, just back to back, very quickly. So that is a very simple example of ForEach. It's enough for us to understand at this point in order to move forward. So as we move forward, the next thing to understand is the yield keyword. So what is the yield keyword? Well, the yield keyword indicates that the method it's within is an iterator. So that means that that method is iterating over a collection of something. It also returns the current value immediately. We'll see that example shortly. And it stores the position of the method's state. That will also be something I'll show very shortly as we go to the example. So some example usage. So we have yield return in some expression. So that expression can be just a number, an integer. It could be a string. It could be the results of a method call. It could be a new class that it's constructing. Anything that's a valid expression. Or you can yield break. We're not going to use that much here, although it's certainly applicable to coroutines. If you do yield break, it ends iteration immediately at that position. There will be no more items in the collection or in the iterable at that position. So let's see an example of yield and how it differs when yield is used as opposed to when we don't use yield and we use the example that we had for the last example. So the first thing I'm going to do is I'm going to make the construction of the test class much more expensive. So every time we construct a test class now, it's going to take us a full second to construct it. So we have to construct 10 of these. So overall, we know that the entire functionality of our program is going to take at least 10 seconds to run now. So if we're going to do this, if we're going to cost 10 seconds every time we construct them, and we're looping over each one and printing it out, how do you expect this to work? Do you expect to see each item written one at a time, 1 second apart? Or what do you expect? So let's run that quickly before we move on to using yield and see what happens. So we've started our test, we're running, and you can see nothing's happened. We're just running. And there we go. We hit 10 seconds, and now we returned them all. So why is that? Do you fully understand? So if you look at it, if we think about it this way, so this method is getting called to get the objects. That method builds up a new collection of type list of test class called results. It constructs all 10 items back to back, and then it returns the collection back. So until it gets to this return line, this method doesn't know if you're done with that collection, if you've built it up the way you want. You could be adding a bunch of items, and then at the end you're going to sort them. So by the time that it gets to the end, they could be in a completely different order. So it can't wait, or it can't provide any data until it's gotten to the final return where it says, okay, I know everything is locked in. This is exactly the way in the order that it needs to be returned, and now I can loop over it. So that's how the ForEach loop as it stands works. So let's see what happens when we change to using a yield. So let's get rid of that example. Let me save this. And let's look at what we did here. So I'm going to add this as a second vertical document so you can see the two side by side. So here's the ForEach test we just ran. And here's the same example using a yield. And if you can see, everything up until this point here is identical. Then we get into this point, and you see we don't construct a new collection anymore and populate that collection and return it. All we do is we loop from 0 to 10 just like we were before, but we yield return each object as we get to it. Now, this is where things get different. So when the for each loop comes along now, it says, okay, I have something that I can iterate over and I can get all of the items I need. But when I get to the beginning, I really only need the first item in order to move forward. So when it gets into calling this code, it's going to come in and it's going to get to here and it's going to say, okay, I've yield returned a new test class of 0 in this case. Well, I know what my first object is. I'm saying that this is the first object. So at that point, this code can continue and it moves forward with that first object without having calculated the other 8 or 9 in this case objects. So this method can continue immediately as soon as that first object is generated. And what happens is yield then stores that this was currently 0, I was 0, and I was at this point in code. Now return that item for the iteration. For each will run that item, so this will print with 0. And then it'll come back up and say, I need the next item. And that will tell it to continue from wherever it was, so right here, with the state of this method the way it was. So I will still be equal to 0 in that case. So it's going to get to the end, and it's going to come back to the top. It's going to increment, and then we're going to return 1. So in order for... that's bad terminology. So now if we run this example, we should expect to see each item returned 1 second after the other as we run through it. So let's run this quickly. You can see we see exactly that. 1 second gap for each one as we run through it. So we're yield returning a new one once a second. Now, it's probably already evident that this is beneficial in many cases. One great example is if you have a loading screen or something to that effect, you don't want to have the thing pause and do nothing for the beginning of the screen, and then all of a sudden at the end show 100%. That's not useful to anyone. Another item to think about is if you have a huge collection, let's say it's a collection of 1 million numbers. Well, it's highly likely that the person using that collection doesn't necessarily need all 1 million numbers. Maybe they need the first 10. They're only going to show a page of results if you're using some kind of business application, which obviously this is a game coding course, but keep that in mind. If you have a page of results, you might have 10 items you need. Well, why generate 1 million items only for the person calling my method to only need 10 of them? In this case, we only incur the cost of constructing the items we actually need. So if we only needed 3 and then this guy had a break in here after the first 3, we would only generate 3. We wouldn't actually call the constructor for the other 7 items. It would save us a lot of computer power. And oftentimes in mobile games, that's really important. So let's look. Let me put that back here. So that kind of explains, I think, enough at this point about what yield is doing. So if we think about it, yield return returns the value that it generated here instantly back to the caller, and it holds its position. So the next time that it's called, it will continue in that exact same spot. So now let's talk about the IEnumerator interface. So keep in mind, up until this point, we've been using IEnumerable, not IEnumerator. So what is the IEnumerator interface? Well, the IEnumerator interface contains 3 methods, but only 2 of them that we really need at this point. It contains a method for getting the current value of the enumeration, and it contains a method for moving to the next value of the enumeration. In addition, it contains a method for resetting the enumeration, which oftentimes isn't even implemented, but it can be implemented to move back to the beginning. So if we think about it, this is very similar to what you would use in looping. You would say, okay, move to the next element and then give me that current element, and then move to the next element and give me that current element. So this is used in many loop situations. So let's look at an example usage below. So in this case, we're saying, okay, give me an IEnumerator called enumerator from some method. So we're calling this method getEnumerator. Let's say that method returns an enumerator to a list of, let's use the same example, a list of odd numbers, integers. So this IEnumerator called enumerator knows how to go through a list of odd numbers. Let's say the first 10 odd numbers. So that's what this IEnumerator knows how to do. Remember, it only has these methods, move next, current, etc. So what we're going to do is we're going to say, okay, while move next returns true, so move next will return true as long as there was a yield that we had another item we could move to. So it starts off pointing at the item before the first item, so it's pointing at nothing. So the first time we call move next, it points to the first item, so it's going to point to 1 if we're talking about a collection of odd numbers. So now, as soon as we call move next for the first time, we have current being 1. So we come in here and we call some function with the current, which is now 1. And then when we get to the end, we come back up to the top and we call move next again, which moves that pointer or that enumerator to the next item in the collection, which the enumerator knows how to do. And now current is going to be equal to 3. And as we run the method underneath, current will be equal to 3, and we can run the function again. So that's a very simplistic overview of IEnumerator. Let's look at an example back in the Visual Studio Code that we had been working with. So let us update and remove the ForEach test with yield and add the IEnumerator test. So the IEnumerator test should look very similar to what you saw in the previous test. The actual bottom IEnumerable get test objects looks very similar to the fact that we're returning an enumerator now that returns the test object's enumerator, but we're still returning a yield returning each object one at a time the same exact way we did before. So we can return an IEnumerator that way, and an IEnumerator will be generated behind the scenes by C# when we have a method that uses yield return in it. It's magic C# isms in that case. So all we have to do is have any method that yield returns objects and defines itself as returning an IEnumerator, and this will automatically work. So at this point we can say, okay, in our run method, instead of just having a for each loop right at the beginning, let's get that enumerator from this method. So now we have an instance of the enumerator that knows how to go over the collection that our get test object enumerators is generating. So it knows how to go through that collection, through all the items until it gets to the end. So as we showed in the example, we're going to call, okay, while the enumerator move next, so that's going to move the first time into the first item. As soon as it hits move next, that tells this method it needs to run until it gets to a yield, and then update the value that it maintains internally as current to whatever that first value that it yield returns is. So as soon as move next is called, now enumerator.current is going to be set to this value, this new class sub 0. So we're passing 0 the first time. So as soon as we call this, it's going to run this method, it's going to run to here, and it's going to say, okay, got to a yield return, stop right there, take the object that we're returning and store that so that we have it when people ask for the current. And we're going to go inside the method, it's going to print using enumerator.current, it's going to continue, and then it's going to come up here and it's going to call move next. As soon as it hits move next, then it comes back in here and says, okay, we were here, so go back to where we were. I was equal to 0, so store that back in there and continue. So we're going to go down, we're going to come up, I is going to increment to 1, we're going to hit yield return new test class 1. Everything is going to pause there again. It's going to store this value into its current, and it's going to continue up here. And so we're going to have enumerator.current equals test class 1. So if we run this, we should see identical functionality to what we saw with our last test. And as you can see, we still have the same pause. We have the sleep in there still, and we're seeing 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. So now we're using IEnumerator, and we're returning by using yield return, just as we saw in the Unity coroutine example. And I don't know if that was obvious when we were working our way to it, but if we take a look right now at the Unity coroutine example, we have a method that returns IEnumerator, and then periodically yield returns something. We're going to talk about this something in a minute. But periodically it yield returns something. So our example is returns an IEnumerator, and periodically yield returns something. So we've now created the exact same functionality we expect to see in our coroutine. So can you see where this is going yet? Maybe you can't, and let's hope that this next section clarifies that. So let's create some coroutines from scratch in Visual Studio without using Unity at all. Let's create a coroutine engine similar to what Unity is probably doing behind the scenes from scratch. So what I'm going to start with, just as an explanation, is we're going to jump over to this documentation. So Unity has a game loop. We talked a little bit about game loop at the beginning. It has a 60 frames per second. So you heard frames per second or some looping mechanism. So if we look at the game loop that Unity has for each object, this dark line here is in essence the game loop per object. So it's going to run all of these methods from beginning to end. Then it's going to go to the next frame, and it's going to come back up, and it's going to run the methods over again. So if we look down here, right here, we're going to see some lines that say, if a coroutine has yielded previously but is now due to resume, then execution takes place during this part of the update. Sorry, I needed a drink. So that's interesting. That means after update, it's going to go and it's going to go through all the coroutines that it has and see if any of them are ready to run. If anything is finished its wait, its pause, and then run the code for its coroutines at that point. So that's interesting. Now if we go to the bottom here and look at the coroutines section, we can also see that it says normal coroutine updates are run after the update function returns. A coroutine is a function that can suspend its execution, or yield, until the given yield instruction finishes. And then it shows a few different types of yields that you can do in Unity. But it mentions this yield instruction, so that's interesting. That means the thing that is returned when you do a yield return is a yield instruction, or what they're calling a yield instruction. So what is the yield instruction? That's something that hasn't been mentioned to this point. So in my example, as I'm creating a new example of how coroutines can work, I created this yield condition, which is similar to what their yield instruction is. It's an interface that says, have I been satisfied yet? So let's think about it this way. All of those things that say yield, let's yield for 6 seconds, yield until the end of the frame is done, yield until some variable is set to true or false, yield until a web request has completed. All of those things have, at some point, they're done. They know that they've completed what it is that they're waiting for. So this interface that I'm using for my example does that. It says, okay, I have a property that at some point will say that it's satisfied. It has finished waiting for however it's supposed to wait. And I've created a few different yield conditions that are similar to ones in Unity so that we can use them. So wait for end of frame, for example, is I think exactly a copied name of one of the Unity ones. And in this case, I'm just returning true automatically. So I'm only actually checking once a frame for a condition to be met. So by the time I check, it will be the next frame. It's automatically satisfied and it'll run the code. Another example is wait for seconds real time. So when this one is constructed, we're given the amount of time to wait in seconds. So I store the current time and the amount of time we have to wait. In Unity, they probably are using the time updates because I believe, well, there's two options. There's wait for seconds and wait for seconds real time. In wait for seconds real time, they could be doing something similar to this. In wait for seconds, they use the current time clock, which can be sped up and slowed down. So they're probably using the actual frame time to do that. But this is very similar. So we're storing the current time and the amount of time to wait. And we're saying that we're satisfied when the current time is greater than or equal to the starting time plus some number of seconds that we've passed in. So if we pass in 5 seconds, if now is greater than or equal to whatever the time at the beginning was plus 5 seconds, then we're satisfied. We've waited long enough. In addition, there's an example in Unity that lets you pass in a method or a lambda that says, I want to wait until something happens, until this method returns true. That one's even simpler. So we take in a function that is going to return bool, and we store that function. And every single time that it checks to see if it's satisfied, we literally just return whatever the results to calling that function are. So if it says wait until a is equal to 13, then every single time that we get to the end, we call the function that compares a to 13, and they're going to pass us a function that does that. So really simple stuff. So let's see, did I update? I haven't. Let's update to run the coroutines test. And let's look at what the coroutines test does. So for my example, I'm storing a list of coroutines. So these are all the coroutines that are currently active in the system in my example. So we have some number of coroutines running. In Unity, it could be thousands. It's really kind of irrelevant. It's smaller scale is easier to explain. So in Unity, there's some game loop. We just looked at that in the website. So I'm going to create a single coroutine that is going to run task 1. That run task 1, if we take a peek at it down here, returns IEnumerator and has yield returns in it. It's exactly the same as Unity would expect. So I'm going to start a coroutine for that. So what I do in my start coroutine is I'm initially calling move next, which isn't exactly identical to how Unity works, but it makes it easier for my explanation. So that's going to run to the first yield every time automatically. So you'll see all of my examples have this first yield return right at the beginning that waits for a very small period of time. And then it's going to add it to the coroutine list to say, okay, every time we check coroutines, that's one of the coroutines that needs to check to see if it's ready to run. So start coroutine is really simple. Realistically, in the real Unity version, it probably would only have to do the add and then make sure that it checks to see if it needs to run immediately, because you can yield return another start coroutine. So it doesn't return void. There's some other stuff that happens there, but this is enough to explain it for now. And so then we are going to run our game loop. So in Unity, this is the main game loop that we explained. In mine, I'm just going to keep running it until we're out of coroutines to run. And we're going to, in Unity, we would run all of this stuff up through update. So we read the little document. It said after update is complete is when we would check and run any coroutines that are ready to run. So all of that processing would happen right here in this example. Then we're going to go through all of the coroutines that we have and see if any of them are ready to run. So I'm going to start my initial index at 0. We're going to loop through until we go through each one. Instead of using an actual iterative for, I'm just doing a forever and then breaking out when I get to the end. It seemed to me to be easier to explain, although that's arguable depending on who you are. This might be confusing. So if we got to the end, if the index that we're on is equal to the count, so if there's 3 items, it should be 0, 1, and 2. So if index is 3 and the count is 3, then we're past the end and we need to break, and we'll come back here next time around. We retrieve the current coroutine for this iteration, so give me the current IEnumerator from that array, so all of our enumerators that we have, all of our coroutines, give me the current one. Then for the current one, get the current value, which we know is an IYield condition. So we're going to yield return one of these guys, which all implement IYield condition. So the thing that we're going to get from current is going to be something that tells us whether it has finished waiting yet. Is it ready to go forward? So we are going to get the condition from the yield condition from the current one. So now we're going to take that current yield condition that we're on for that coroutine and see if we are satisfied. Has it waited long enough? Is it ready to run the next piece of code? So if it has satisfied, that means we've waited long enough and we're ready to run some more code. We're going to call move next on the enumerator. And remember, as soon as we call move next, it's going to jump back into the code that had yielded before, wherever the yield was in the code, and continue forward until it gets to the next yield. And that's how we get that multitasking functionality, is move next actually runs code. It's running the next piece of code until it gets to the next yield. And the next yield will return to me, how long are we waiting until we do it again? So that is the thing that gets returned. So one of the other things that move next actually directly returns is whether there's anything more to do. If there's anything left in the iteration, is it the last yield? Is there nothing left? If there isn't anything left, I'm just going to remove the coroutine from my collection. There's nothing left to do. And we're not going to increment the index, because if we removed item at space at index 3, then the next time around I want to check what is now index 3, because index 3 was removed, so everything slid down a spot. So now there's a new index 3. If we didn't remove anything, if we hit something and there was another thing to go to and it was still in our list, then we're going to move on to checking the next one up. So we're going to check index 4, for example. And the same thing if the condition wasn't satisfied. So if we have 4 coroutines and the first one isn't ready to go yet, then we're going to go check the second one and see if that one's ready to go yet, and do that until we get to the end. So this is our current coroutine run loop. It's very simple. There's a little bit of understanding what a yield condition is and how current works, but once you've got your mind wrapped around it, it's pretty direct. So let's see if it works as we expect. So run task 1. So like I said, normally we wouldn't have this in the Unity world. This is just something due to the way that I've implemented it so far. So we're going to look at this section. So we're going to yield return a wait for 5 seconds. So we're going to wait for 5 seconds. We're going to log another 5, log another 5, and log. So since that's the only coroutine we're going to insert at the beginning, that's all we should see. So let's see if that's the case. Let's run this one. Here we go. So we started at 10 seconds after 15 seconds, so that's 5 seconds. 20 seconds, an additional 5 seconds. 25 seconds, an additional 5 seconds. So we got the functionality exactly as we would have gotten with Unity coroutines, doing basically the same thing. I mean, the a method that returns IEnumerator. We're yield returning a wait for seconds and then putting code in between it. So pause functionality for 5 seconds, do some code. Exactly as you would expect to see in Unity coroutines. Let's make sure that we haven't actually just replicated something like a sleep. So keep in mind, if we were to do a sleep in here, then we would be holding that thread and no one else could run. We couldn't interleave work. We couldn't get other threads or other processes to work. And the whole idea here is to have single-threaded multitasking. One thread that can run lots of tasks by giving each task just enough time to do what it needs to do every frame. So now we're going to run both task 1 and task 2. And what we should see, if we look at these closely, is we're going to see 5 seconds and then the first, 5 seconds in the second, 5 seconds in the third for task 1. It's pretty simple. Task 2 is going to run a whole bunch of stuff right at the beginning. 6 items right at the beginning with 1 frame in between, which in the frame times that we're getting from ours is going to be nearly instant, within the same second for sure. Then we're going to wait 6 seconds and run item 7. So I would fully expect to see all of these appear. Then this one, since it only waited 5 seconds, this should appear. And then since this waited 6 seconds, this should appear. If that happens, we are truly getting multitasking on that single thread. We've never created new threads, keep in mind. We're just trying to run multiple tasks off of the same thread. So let's save that and let's run it. Sorry, it's running off screen to start. So we did see our first 6 appear immediately. Then we jumped to task 1 and saw step 1 because that happened after 5 seconds. And then jumped back and ran step 7. Here we go. After an additional second, so after 6 seconds. And if we looked at the timings, they should be relatively close to what we want, and it looks like they're exact. So we had everything here run at 11 seconds after. Then we had a 5-second gap before we saw this guy, and then an additional second. So this was a 6-second gap here. So an additional second before we saw that guy, and then 5 seconds between these. Exactly as we expected. So we are creating that coroutine feel directly without using any of the Unity magic at this point. So one final demo. Let's remove these guys. Oops. Let's remove those. Save that. Let's see what those two methods do. So I'm going to be running these two at the same time. So what do we have here? So we have, remember we're looking at this section. So this guy waits for 5 seconds. Then it's going to log that it's providing value for task 3 release. And it's going to set this flag to true. So it's initially false, and it's going to change it to true. And that's all this coroutine is doing. This other coroutine that's running at the same time and sharing the same task space is going to start out by first saying that it started. Then it's going to yield return a wait until this method happens. So this happens. Return wait flag equals true. So when wait flag is true, when this returns true, then it's going to run this method. So we should see this only turns true immediately after this happens. So we should see this. Then we should see at some point this happening. And as soon as this happens, very quickly thereafter, we should see this, because this is setting the variable that this guy is waiting for. So let's see if that functions as we expect. There we go. So if we can look, okay, 21 seconds after, we got the initial start here. Then we waited 5 seconds as we expected. Oops. 5 seconds, and we logged that we were about to set the release value right here at 26 seconds after. We set the value, and then instantly afterwards, this was determined to be true, and it returned back to this method and ran this final piece, which it did. So we got exactly the functionality we expected from wait until, and this matches very closely to what Unity's wait until looks like as far as signatures go. So very similar. So that's really all I had to explain at this point. I just want everyone to have a better idea of what coroutines are really doing. A lot of people feel like coroutines are magic and don't understand what IEnumerator meant, and why is a coroutine returning an IEnumerator, and what is this yield thing. So I hope by going through this video, you understand all of that just a little bit better. If you have any additional questions, feel free to add it to the video. I'd love to answer them. I'd love to create new videos that explain other things you find difficult. I'm really interested in this teaching portion of game development. I've been doing game development, or at least programming, for a very long time, and I'd be interested in helping others get into the industry or just get better at their programming and their indie design challenges. So feel free to join visit me on my website, join my Game Code Plus Discord. The link's there. And visit the YouTube channel, which you're probably watching this video on, and like and subscribe if you found this helpful and interesting. And thank you very much. I appreciate you spending your time with me today and hopefully learning a little bit more about Unity and coroutines.